Okay guys, just to follow up on our lesson from today, I thought I'd repeat the instructions for modeling with a sinusoidal function, any sort of periodic motion, and periodic motion is motion that repeats itself. So looking at the classic Ferris wheel problem, something you're guaranteed to get on a test or exam, we have to read carefully at the materials given because they give us a lot of information. First and foremost, it takes 32 minutes to do a full rotation. So that tells us the period. And so our period is equal to 32 minutes. And also a little bit higher up on the page, we'll see that people board at a height of 5 meters and get to a max height of 135 minutes. So if they're boarding at 5 minutes, we have to note that there's probably some sort of platform here where they board with a height of 5 meters, and the total height is going to be 135 meters. Now we can calculate the amplitude using this information, and the amplitude is simply the radius of the circle. So if you note 135 subtract 5 gives us the total diameter of the circle, which is 130. Halved is the radius, which is 65 meters. The formula that could give us this information for amplitude is max minus min divided by 2. And in this case, it would be that same calculation, 65 meters. Notice that the amplitude is the same thing as the radius, right? So radius equals our A value. We can also look at where the axis of the curve is by looking where the middle of the circle is, because that is sort of our quarter points. And you'll note that these are 70 meters off the ground. And we could have calculated that using a formula, looking for the axis of the curve by adding the max plus the min divided by 2, otherwise known as their midpoint, which makes sense because that's the middle between the midpoint between 5 and 135. So doing that as a calculation over here, we would have 135 plus 5 divided by 2 is 140 divided by 2, which is 70 meters. So looking at how the motion actually moves, we'll note that here at time is equal to 0 minutes, we have a height of 5 meters. And here at the very top, which is halfway around, that would be time is equal to 16 minutes. We got that because it's 32 minutes for a full rotation. We're going halfway around, so that's 16 minutes. And our height is the max height, which is 135 meters. So we have a ton of information here, more than enough information to actually graph this. So let's do that. So let's label our boxes now. So each of these boxes along the horizontal axis, which is going to be our t in minutes, will be worth 2 minutes. So I'll just label every other one: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And there's our full rotation covered. And then our vertical axis, which is going to be the height based on time in units of meters. So here we have our height and our time, and now we can plot our key points. Oh, right, forgot to label the axis. So each of these boxes I'll label as 10, starting from 0. So it'll be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, and that's enough. We're already gone beyond the max height, so we don't need much else. So let's graph our key points. So starting at 5 meters at time 0 is right over here, that guy there. And at the end of our time period at 32 minutes, we're back at the same height of 5 meters in total. Halfway between, like we said at 16 minutes, we're at 135 meters right there. And at the quarter points of the circle, we are at 70 meters. So that'll be halfway between 16 and 0, which is 8. And that is 70. Actually, it'd be easier if I just graph the axis of the curve through 70, because we know that's where we're actually hitting. So there it is. And I should label that as well. So H equals 70. Oh, how convenient that that 70 is right there lined up perfectly, and I don't have to write it again. So now at 8 minutes, I can plot that point, and at 24 minutes, which is the other quarter point midway between 16 and 32, is that again. Another way you can find these using that interval idea we talked about, where we take the entire period and we divide it by 4, and that tells us how long it takes for something important to happen. So minimum to axis of the curve, axis of the curve to the max, and then back down again are each quarter periods, or 8 minutes. So I will graph this now, draw my curve as smoothly as I can through each of my points, continuing it off the graph with an arrow to show that it continues. So now I can actually use the plotted curve to model with a function. And so I'm going to start with the cosine function, because if you notice, cosine function would normally start at the maximum going down, but since I'm at the minimum going up, this is actually an upside down cosine function, so I can just vertically flip it with a negative, add in my amplitude, function cos, and I need my horizontal stretch, which is k, which is 2 pi divided by 32, which simplifies to pi over 16. Where did that formula come from? We talked about it in last class, where the k value is 2 pi divided by the period. Remember, we use 2 pi, not 360, because we're working in radians. So pi over 16 is the value that ends up in here. And you'll note we do not have to horizontally translate this. There's no phase shift because it starts perfectly upside down at 0. So I just add in my x, and then I do my vertical translation plus 70. Alternately, I could have started from the normal behavior of a cosine function by looking at where the max is going downwards, because that's what a cosine function untransformed normally does. And if I would do that, I would have to horizontally translate it by a phase shift of this distance, because normally it would be at 0, but now it's happening at 16. So I'd have to shift it to the right by 16. And so that function could look like this. No vertical reflection anymore, so positive 65 cos. Notice I'm going to keep the pi over 16 separate from x and the horizontal translation. That's pretty important. I'm going to subtract 16, even though it moves to the right and subtraction feels like it should go to the left. X lies to us, so that's what we're doing. Plus 70 is the same. Modeling with a sine function, we can actually take a look at where the sine function's normal behavior is, which is on the axis of the curve headed up, which happens right here at 8. There it is. And this distance here is our horizontal translation for sine, which is 8. So most of the information is the same from cosine to sine. I would say my function for sine is g at x is equal to my amplitude 65. Notice it's positive because I haven't flipped over sine, multiplied by sine. In brackets, I have pi over 16 separated from x and the horizontal translation, which is x minus 8. And then outside the function, I have my vertical translation plus 70. So there we have 3 possible functions, and there are way more that you could actually use, but these ones are the easiest to generate. Now we can use the graph and the functions to answer the questions below. And at what time is the height of 120 meters? So here's 120 meters. My graph is a little off, but I could also take 120 and substitute f at x for 120, solve for x. Might be easier with this one by moving the 70 over, dividing by negative 65, inversing cos what I have here, and then dividing away pi over 16 to find the value of x. Should have actually crossed over here at 12, and again, it would have crossed over here at 20 as well. So we're at approximately 12 minutes and 20 minutes would be the answer to those ones. If your graph is a little bit inaccurate and you answer based on your graph, that's okay, but it doesn't hurt, and it only takes another minute to actually use the functions you created to check your answer, because everything should agree with each other. And we're pretty close to 12 here. So if I were to do that reverse calculation as I described, I should end up in the same spot. If I were to raise it up by 7 meters, well, that's just a vertical translation. So instead of up by 5, which is what's happened here, or actually by 70, because that's where the middle is, I would just add another 7. So the vertical translation or axis of the curve would shift up by 7 more meters. Translation, which is the axis of the curve, increases